Okay, hello everyone. Yes, like last lecture, we shortly considered magnetic field flux concept, and I believe this lecture will start with a short reminder. We'll solve one example of calculating magnetic field flux next to a straight long wire. And then we will proceed with a new topic, which is magnetism in matter. So we'll consider different, like origin of magnetism in different materials, and also consider different classes of materials in terms of their magnetic properties. In particular, we'll consider ferromagnetic materials, paramagnetic, and diamagnetic materials. So let me change the camera, and let's refresh what we did last time with introducing the magnetic field flux. So let's say we have certain surface with a small element on this surface. Here we have vector dA, which is defined by the direction of the unit vector, normal vector to this surface element, and its magnitude is equal to the area of this segment. And also we have vector B, which is magnetic field vector, and there is certain angle theta between these two angles. So magnetic field flux through this small segment could be represented as a scalar product of magnetic field vector and dA vector. So that will be in absolute values. We can, well, actually will be scalar number because we have scalar product. So we can continue here, and will be product of magnetic field times dA absolute value of these vectors times cosinus theta between these two vectors of magnetic field and surface element vector dA. So magnetic field flux will be equal to 0 if angle theta is equal to pi over 2 radians, or this will be 90 degrees. So when these vectors are perpendicular to each other, magnetic field flux through this surface element dA will be equal to 0. Magnetic field flux reaches its maximum value, which will be amplitude of magnetic field vector times dA, the area of this segment, when this angle theta is equal to 0. So in this case, if they are parallel, these two vectors, then magnetic field flux will be will gain some maximum value. So obviously, if we want to know magnetic field flux through whole surface, we need to integrate. Total magnetic field flux will be integral over this surface of scalar product magnetic field vector dA vector. And we need to define also units for magnetic field flux, which is Tesla times square meter. And this magnetic field was designated as specific unit. Magnetic field flux is measured in specific units, which is WB, and this is Weber. So now what we want to do, let us try to consider some specific case for finding magnetic field flux. And for this, we will go to another slide where we will have such a system. We have a long straight wire with electric current I flowing through it. So from this right side, we'll have magnetic field lines going perpendicular to the plane of the image. And let us consider some rectangular frame, segment of area, which has width A, length B, and our task is to calculate magnetic field flux. So we need to keep in mind that magnetic field is not uniform, so it changes with the distance from this magnetic, this straight long wire. So let us consider some small element of this frame at the distance r from the wire, and the width of this small element area will be dr. So now let us try to calculate magnetic field flux through whole area defined by this rectangular frame. So it will be equal to the integral of scalar product, which we mentioned previously. Since direction like normal to the surface of this rectangular frame is parallel to the magnetic field vector, we will get just integral of product of absolute values, magnetic field vector and dA. So we know from previous lectures what will be magnetic field next to a straight long wire with electric current I flowing through it. So we can write integral, instead of B, we will write mu naught times I over 2 pi times R dA. So this dA, first of all, we need to define in another form this differential of the surface and element, like of the area. and that will be side B, like length of the frame, times delta R. So we can write integral mu naught times I over 2 pi R. Then here will be B times dr. So now we need to factor out from this integral all constants. It will be mu naught I over 2 pi. And under the integral, we will have dr over r. So we need to define here the limits from where to where we integrate. And for this purpose, let's consider that this close side of the frame to the wire is located at the distance c from the wire. And in this case, if we have like our axis, let's say x starts at the wire and goes to the right, then we should integrate from c to c plus a, which means that we will integrate all area which is defined by this rectangular frame. So in this case, we will get mu naught times I over 2 pi, natural logarithm. So this integral of dr over r is natural logarithm of r from c to a plus c. So this will be equal to mu naught I times b over 2 pi natural logarithm a plus c minus natural logarithm c. Taking into account features of logarithms, that the difference of logarithms is equal to the logarithm of the ratio, we'll get mu naught times I times b over 2 pi natural logarithm of a plus c over c. And this is equal to mu naught times I b over 2 pi natural logarithm of 1 plus a over c. So this is the final equation, which helps us to allows us to calculate the non-uniform magnetic field flux through the given rectangular frame as shown on our image. So now let us switch to a new slide, and we start with considering magnetism in matter. So obviously, if we deal with matter, we need to start with some building blocks of this matter. So actually, it's this building block is atoms. And let us consider moving like circular movement of electrons around nuclei of an atom. That could be considered as some tiny circular closed current loop. And thus electron, because of this circular movement around nuclei, electron possess some angular momentum, and since it also considers as certain current loop, it will also possess certain angular magnetic moment in the other direction because of the negative electric charge of electron. So let us consider such system. We have some circular trajectory. Electron negatively charged is moving along this circular trajectory. It has some linear velocity v. So this is radius of this trajectory. And from this configuration, we can consider some angular momentum and some magnetic moment. So direction of current for such a tiny loop would be clockwise, because electron, which is negatively charged particle, is moving counterclockwise. So in this case, this magnitude of electric current can be represented as charge of electron over the period of rotation around along this circular trajectory, which could be written as electron charge times linear velocity, like linear magnitude of linear velocity, its speed, and divided by 2 pi times r. So it's actually this period will be the circumference of the circle, will be 2 pi times r over v. So we know how we can quantify electric current flowing in this tiny loop. And also we know from previous lectures that magnetic moment is calculated, it's like absolute value is magnitude, calculated as electric current times area, which is defined by the closed current loop. And in this case, it will be I times pi r squared. So now instead of I, we can substitute its expression. So magnetic moment is equal to E times V over 2 pi r times pi r squared. So this is equal to E times V times r over 2. From another side, we can express the angular momentum absolute value as the product of mass of electron times V times r. And if we now express mu in terms of L, we can get the following equation. So it will be electric charge of electron over 2m(e) times L. So we now have an equation which provides us the relationship between the magnetic moment of this tiny current loop caused by electron moving around the nuclei and its angular momentum. So since, again, I repeat this, electron charge is negative, the direction of these two vectors, of L and mu, they are opposite. So they are parallel to each other, but pointed to opposite directions. So one of the fundamental outcome of quantum physics is that orbital angular momentum is quantized, and it's equal to discrete number of constant, which is equal to h over 2 pi, and this h is the Planck's constant. Since angular momentum of electron in an atom is quantized, that is also true for angular magnetic moment, and the smallest orbital magnetic moment, according to quantum theory, can be equal to square root of electric charge over 2 m(e) times this constant, which is equal to Planck's constant divided to by 2 pi over 2 pi. So since all substances, like all materials, contains electrons in their atoms, it looks like that all materials should be magnetic by definition, because all electrons possess some magnetic moment. However, it's not true, because most of these electrons occupy energy levels of atoms in pairs, and they have opposite magnetic moment vectors which compensate each other. Thus, we have like many electrons, but the net magnetic moment originated from this angular orbital motion of electrons is very often equal to 0. And that's why we do not observe magnetic features of in all materials. So another feature which should be considered of electrons, and also it's true for other elementary particles, but it's in orders of magnitude smaller because of larger mass of protons and neutrons, is such a fundamental property of elementary particles as speed. In classical approach, it's understood as angular momentum originated from spinning of electron about its own axis. Obviously, such motion results not only in angular momentum, which is also quantized, and this angular momentum is marked as S. So the smallest value for this is square root of 3 over 2 times this Planck's constant. And also with this angular momentum originated from spinning, also exists some spin magnetic moment, which is mu spin and is equal to E times H over 2ME. So this me represent electron. Then we will have some axis of rotation, and that will result in an spin angular momentum, and in the opposite direction will be spin magnetic moment. So here, as you may see, we have only constants. Here are 3 constants, and that's why this is used as a also constant parameter called Bohr's magnetron, and it's equal to EH 2ME, and it's equal to 9.27 10 to minus 24th Joule over Tesla. So this is a constant called Bohr magnetron, and this defines the smallest spin magnetic moment of electron. As I mentioned, neutrons and protons also possess this spin angular momentum, and but their magnitude is much smaller because the mass is like 3 orders of magnitude larger than mass of electrons. So now we can make, when we define main contributions in the magnetic features of atoms and thus matter, we understand that the magnetic properties of the atom will be defined by the sum of magnetic, like vector sum of magnetic moments originated from orbital and spin motion of electrons, and it depends how they are compensated or not compensated in particular atom. It will definitely influence what kind of magnetic properties will possess material made of such building blocks. So first we would like to consider ferromagnetic materials, and paramagnetism, like small number of substances exhibit strong magnetic effects called ferromagnetism, and some examples, like classical examples of ferromagnetic materials, are such metals as iron, cobalt, nickel, gadolinium. So these atoms of these metals, they possess some permanent magnetic moment, and what is interesting about them, that because of strong coupling between these neighboring magnetic moments, they tend to align in the same direction and form so-called domains. These domains are kind of clusters of atoms with a number of about 10 to 17, 10 to 21. We have 10 to 17 up to 10 to 21 atoms per domain. And these are under normal conditions without external magnetic field. initially they are each of these domain possess some resultant strong magnetic moment, because all molecules, due to strong coupling between their magnetic moments, are oriented in the same direction. And initially, magnetic moments of all these domains are randomly distributed and oriented. So the net magnetic moment of the material could be equal to 0. So as shown on this image. However, if we place such material in external magnetic field, as shown here, it happens that due to interaction between magnetic moments of separate atoms, the certain domains which had initial orientation of magnetic moment, like net magnetic moment, in the direction of the external field, grow in size, and as a result they increase their net magnetic moment, resulting in so-called magnetization of the material. So this material, because of much larger domains with stronger magnetic moments in the direction of magnetic field, in comparison to small domains in the opposite direction, they provide quite strong magnetic field inside the material, which is stronger than the external magnetic field. And this is the effect of ferromagnetism, when we can kind of amplify, considerably increase strength of magnetic field inside the material because of these features of coupling between magnetic moments of separate atoms and this ferromagnetic domain structure. What is interesting, if we eliminate the external magnetic field, this induced magnetization, magnetic features of the ferromagnetic material may remain for quite long time. So this permanent magnetization is quite important feature because we can make, for instance, some iron or nickel-based alloys. We can magnetize them with strong external magnetic field, and then this is the way how we create permanent magnets. After getting rid of external magnetic field, these materials remain for a long time magnetized and can serve as strong permanent magnets. However, there is certain temperature, which is called Curie temperature, at which this dominant orientation of domains magnetic moments vanishes. So because of large vibration energy of crystalline lattice, this coupling between magnetic moments of separate atoms within domains reduces, and there is a transition back to this randomly distributed, more or less equal size domains in ferromagnetics. So if we heat it up above certain temperature, which is called Curie temperature for ferromagnetic materials, they lose this induced magnetization and come back to its original state. So for instance, Curie temperature for iron is very high. It's 1000, like over 1000 Kelvin. So we need to heat up this temperature, this material to high temperature in order to reduce, to get rid of this induced magnetization. But it's not true for all materials. For instance, gadolinium, it's enough to heat it up only to 317 Kelvin, which corresponds to 44 degrees Celsius. And then this induced magnetization, the ferromagnetic effect, will be gone. So this is what I wanted to tell you about ferromagnetic materials. Another class of materials is, in terms of their magnetic properties, is paramagnetism or paramagnetic materials. And one of the example of paramagnetic material is liquid oxygen. So if you see if it's poured on top of permanent magnet, liquid oxygen tends to be attracted by poles of this magnet. So why it happens? Paramagnetic substances have weak magnetism resulting from the presence of atoms or ions that have a permanent magnetic moment, similar to ferromagnetic materials. However, they don't have such strong coupling between two neighbors, like neighbors of neighboring magnetic moments, and that's why they do not have such predominant orientation in the same direction as we can observe in ferromagnetic materials. So when we place such paramagnetic material in external magnetic field, these separate atoms tend to orient along the external magnetic field because of their permanent magnetic moment. However, since there is weak coupling between neighbors, we don't get such strong magnetization as in ferromagnetic materials. And also we need to keep in mind that this orientation of separate atoms, like orientation of their magnetic moment vectors along external magnetic field, will always compete with vibration, like thermal vibrations. And that's why it's very difficult to have a very strong orientation of all magnetic moments of atoms along one direction, which is defined by external magnetic field. So as a result, paramagnetic materials, they enhance magnetic field slightly, so they slightly increase magnetic field inside these materials and are attracted to different poles of permanent magnets if we place them in between these poles. However, this effect is quite weak in comparison to ferromagnetism. So the third class of magnetic materials are diamagnetism or diamagnetic materials. So first of all, I would like to highlight that all materials possess diamagnetism because it's a feature of interaction of moving electrons with external magnetic, like change of magnetic field. However, if material possess ferromagnetic or paramagnetic materials, so if atoms already possess some permanent magnetic moment, and moreover, if these magnetic moments are coupled with each other, then diamagnetic effect is much weaker and it can be just neglected. However, if atoms of the material do not possess this permanent magnetic moment, then diamagnetism should be taken into consideration. So if we, when an external magnetic field is applied to a diamagnetic substance, a weak magnetic moment is induced in the direction opposite to the applied external magnetic field. So that is happening because of effect of external magnetic field on the movement of electrons in around atoms. So some change of magnetic field causes increase in this current through this very tiny current loops, which are created by electrons. We will discuss this in more details a bit further, some effects related to this. But the in general explanation is that external magnetic field causes electrons to move faster around nuclei of atoms, and this change in this increase in the loop current created by electrons generates certain additional magnetic field in a direction opposite to the external magnetic field, which is placed where this diamagnetic material is placed. So ideal example of diamagnetic material is like some ideal diamagnetic material is superconductor. So if we what we see here on this image, if we place some permanent magnet on top of a superconducting material, which is cooled down to liquid nitrogen temperature, then this permanent magnet can just levitate without touching the surface of the super magnet. So this happens because like permanent magnet definitely creates some magnetic field around it, and superconductor, this presence of magnetic field can cause reaction of response of electron current, like these loops in the current loops in the superconductive material without any losses in energy, because they don't possess any resistance to electrons don't possess any resistance in moving in superconducting material, and that's why in superconducting material this induced current loops can fully screen external magnetic field. And one of the conditions for existence of superconductivity is that magnetic field cannot penetrate into the superconducting material. So that's why all magnetic fields are kind of repelled from the superconducting material. And in this case, we have compensation of gravity force with this repelled magnetic field generated by permanent magnet. So this could be done not only with similar levitation experiments can be done not only with superconductors, but also with other diamagnetic materials. For instance, this is a famous experiment of levitation of a live frog in strong magnetic field because of diamagnetic features of water molecules, which are in large quantity inside the tissue of a live frog. So this frog is levitating in strong magnetic field. And this experiment was carried out by Andre Geim. So while he was working in Netherlands, for this experiment in 2000, in year 2000, he received so-called Nobel Prize, which is kind of funny version of renowned Nobel Prize, and it's given to scientists who perform some trivial but extraordinary experiments, and when results are kind of exciting and make people laugh on them, and then they start to think what kind of physics or chemistry is behind this trivial and funny experimental result. What is really specifically interesting about Andre Geim and that he was the first scientist who managed to get both Nobel Prize in year 2000 and also Nobel Prize for invention of two-dimensional material graphene in 2010. So this is so far only one scientist who managed to get both of these prizes for his research. Okay, with this, I think we are done for today. We are already running out of time. Thank you very much for attention. We will meet next time on Monday. That's why if you don't have any questions, I would like to wish you a good weekend. Take care and see you on Monday. Bye-bye.